I'm going to change gears a little bit in this talk to really focus on how we assess the impacts of our activities and specifically look at a couple of examples from the energy industry. But before that, I just wanted to get started by giving some context about the current discourse around the climate impacts of energy and the role that LCA can play in this context. So many governments and different companies around the world, including energy companies, have committed over the last couple of years to achieving net zero greenhouse gas emissions by 2050. And this was really motivated by a 2018 special report by the Intergovernmental Panel on Climate Change, which said that to keep global warming below 1.5 degrees Celsius, we would need to reach net zero greenhouse gas emissions by 2050, or by 2090 to keep warming below 2 degrees Celsius. And so on the figure here, you can see the trajectory that we have been on is that yellow line in terms of our global greenhouse gas emissions in gigatons per year. And so to meet that 2-degree warming, we would need to start following the red line. And so that includes both massive investments in GHG mitigation technologies. So that's making up that green component of the chart. But then also, because there's some emissions that are just not feasible to decarbonize or eliminate completely, will also require the investment in carbon removal technologies to get to that net zero. And so when we say a net zero system, we're often thinking only about direct or combustion greenhouse gas emissions. So something like an electric vehicle might be net zero on site, but it isn't net zero when you consider the full supply chain. And so to get true net zero, you need to include both those scope 1, 2, and 3 emissions, and think about the whole system within which your technology is operating. And so that would also include scope 2 emissions, so the indirect emissions from electricity supply, as well as scope 3 emissions, which includes the upstream and downstream supply chains and end of life of your product. If we look at Canada's greenhouse gas emissions, in 2018, Canada emitted 728 megatons of CO2 equivalent. And if you look at the breakdown by sector, you can see that electricity was only 9% of the emissions of our national emissions. And the majority of our emissions actually come from transportation, oil and gas, and the building sectors. And so within those greenhouse gas emissions in the other sectors, some of those emissions are non-energy related. So things like material or the embodied carbon, embodied emissions in cement, for instance, and building materials, but a lot of them are related to the non-electricity energy consumption in those sectors. So on the right, you can see the energy demand by fuel for Canada in 2018, and you can see that electricity is actually only 17% of the total energy demand in 2018, and that the majority of that energy demand was actually met by refined petroleum products, so things like gasoline and diesel, and natural gas. And so decarbonizing, getting to net zero, will require that we address the greenhouse gas emissions, not just from our electricity supply, but also from how our demand for fossil fuels, as well as those embodied emissions. And that's complicated because getting to a net zero electricity grid is just really not far enough to meet those targets. But we can't just today eliminate all fossil fuels because we don't have the infrastructure in place to provide zero greenhouse gas emissions energy to our different sectors. And so to do that would require a lot of investment in infrastructure redesign and new technologies. But the question then is, what what do we know what changes should we make to get the biggest benefit? And where should we prioritize our changes to meet our decarbonization targets? And that's where life cycle assessment comes in. So understanding how to make this transition requires a systems perspective. So it means not just looking at that direct emissions or the direct site, but taking a step back to look at the whole system and the interaction between the system and other systems in the environment. Life cycle assessment is a systems tool, so it's one means for doing a systems analysis. And it assesses the environmental burdens of a process, product, or system over its full life cycle, what we call from cradle to grave. And so you can see an example of a cradle to grave on the right here. And so that's considering from material extraction through manufacturing, transportation, the actual use phase of the material or product, and then through to disposal or recycling. And so life cycle assessment, the first LCA was conducted in 1969 by Coca-Cola. And they were looking at trying to figure out what would have lower environmental impacts on glass or plastic bottles. Over the next 20 years or so, there were a lot of product focused life cycle assessments that did those types of comparisons. So a common example would be something like comparing plastic, disposable to reusable cloth bags to paper bags. And there was a lot of questions around the results and recommendations coming out of these life cycle assessment studies and concerns about the robustness of the methods employed and the kinds of assumptions that were being made to draw those conclusions. And so to address those concerns, in 1977, the International Organization for Standardization published the ISO 14040 guidelines. And these are a framework, provide a framework for life cycle assessment with the objective to increase the consistency, transparency, and robustness of life cycle results to help give the public and readers of LCA studies more confidence in the results and recommendations coming out of those studies. If we look at the ISO framework itself, it's a 4-phase framework on the left. And it starts with something called goal and scope definition. And this helps you look at framing your study to say, why do you want to do this study? So what's important? What question are you trying to answer? And then how are you going to scope the study? To do that, you have to define your system boundary. So say which activities will be included or excluded from your system. You need to think about the temporal scope. So whether you're looking at a study about something happening today or into the future. And then it's also defining a functional unit. And so if you see life cycle assessment results, they're often presented, say for electricity, you would be looking at per greenhouse gas emissions per kilowatt hour of electricity delivered. And the functional unit provides a consistent metric or measure so that you can compare different product systems on a common basis. After goal and scope is the inventory analysis. And this is where you would go out and actually collect the data about each different operation within your system to get the process unit mass and energy flows. And you would use that to build out your system. And then you would start modeling the inputs and outputs from the system by multiplying those energy flows by emissions factors. So things like the carbon intensity of the electricity supply. The next phase is the impact assessment, and that's where you take the individual flows from the inventory analysis and you relate them to a final emission or environmental impact of the system to give you something that you can actually evaluate and use to make comparisons. And then the last stage, it's an iterative process, but the last sort of step after each phase is interpretation. This is where you look at your results and you think, what kind of conclusions can I actually make from this study? And is there anything missing from the study, or are there any uncertainties? or areas where I should go back to maybe the goal and scope or the inventory, revise my research question, or collect more data, say, to help give me more confidence in the answer. Going back to the evolution of life cycle assessment, after the standard was passed in 1997, the biggest change in the next 20 years, or so the last 20 years of LCA, has been the use of LCA in policy, and particularly in energy policy development. The most notable of these was the California Air and Resources Board, which in 2007 enacted the low carbon fuel standard. And the standard was the first standard to actually embed life cycle assessment results in policy. And so the standard was enacted in 2007. It began in 2011, and it set a goal of a 10% reduction in the carbon intensity of transportation fuels sold in California by 2020, a 20% reduction in the life cycle carbon intensity of the fuel mix sold in California by 2030. And so what that actually meant was that each fuel supplier needed to know the life cycle carbon intensity of their fuel. And so this fuel standard meant that overall, for the full fuel mix, they needed to achieve a carbon intensity reduction. And so they weren't picking, say, winners of different technologies. They were saying, however you can achieve that reduction, so whether by reducing the carbon intensity of your existing pathway, blending in other lower carbon fuels, or purchasing offset credits from other suppliers, you need to use one of those methods or all of those methods to meet your reduction targets. And so what that's looked like from 2011, by 2020, there was a 7.5 reduction in the carbon intensity of the fuel. And they're on track to meet that 20% reduction by 2030. Since the enactment of this policy, similar policies have been enacted all over the world, and Canada has a national clean fuel standard that is being adopted. So outside of low carbon fuel standards, how else can LCA help in the energy industry? It can help inform decision making. So if you were designing a product, you could say which aspect of my product's life cycle has the biggest impact on the environment and why. So would that be driving a car, building a car, or fueling a car? And then you can, from that, understand what you should focus on to reduce your environmental impacts. It can also be used to inform policy. So looking at the greenhouse gas emissions implications of wider use of biomass in fuels and plastic. You can answer a question like if CO2 enhanced oil recovery helps or hurts the climate on a net systems basis, or what the implications of electric vehicle adoption would be within a specific power grid. LCA more recently is also being used to assess new technologies. And so this is the focus of my research. And essentially when we're looking at new technologies, we can divide them into two different types. There's technologies that are new, that haven't been deployed in any market, so that would be an emerging technology. There's also commercial technologies that haven't been deployed before that would, you could look at the implications of deploying them in a new market. And so the types of research questions that we would ask are things like how you can adapt life cycle assessment to better assess emerging technologies where the system isn't actually exist yet. You can look at how LCA can better inform the development of early stage technologies. So getting like from the lab scale in and helping to inform that development. Some of the work that I've been doing lately is around carbon capture, utilization and storage, and also different hydrogen applications. And so that concludes my presentation. Yeah, so basically life cycle assessment is a tool that can be used to assess those trade-offs. It is really critical at this point in time because of the scale of transformations that are required in our economies. And it can be really useful in terms of product selection, policy, and technology development.